Okay, so let's move on to this last topic for PNC, which is groupings. Okay, now there are a lot of types of questions in groupings. What I've done is I've tried to identify all the types and break down into a set of questions so that it is easier for you to follow. So let's look at the type 1 and question number 1. Find the number of ways in which m plus n things can be distributed into two groups containing m and n things respectively. The answer is m plus n factorial divided by m factorial divided by n factorial. Let's take this with an example. 10 men are to be divided into two groups, one consisting of 7 men and the other one consisting of 3 men. So what is m here? 7. What is n here? 3. What is m plus n? It is 10. So according to this formula, my answer is 10 factorial divided by 7 factorial divided by 3 factorial. If you look carefully, this is nothing but a formula for NCR, where n is 10 and c is either 7 or c can be 3. Both these are the same thing. Okay, so why is it so? Let's solve this question in another way. I have two groups. I have group number 1 here and group number 2 here. Group number 1 has 7 men and group number 2 has 3 men. For this group number 1, out of 10 I have to choose 7. So in how many ways can I do this? 10C7. Remember, I'm using C here because I'm only selecting these 7 people, not arranging them. I don't need to arrange. So how many places are left? Now out of 10 I've already used 7 people or 7 men. So I have left with 3 and I require here 3. So there is just one way. I can choose 3 people out of 3, or I can write C3, which is nothing but 1. So what is the answer here? 10C7 is what? 10 factorial divided by 7 factorial divided by 10 minus 7, which is 3 factorial. So this is the answer, and I have the same answer here. So this case was nothing but a mere selection of people. So this is the easiest case. Let's move to type 1, but a different question. The number of ways in which m plus n things can be distributed into two groups containing m and n things respectively, but here m is equal to n. Then what is the answer? Okay, the answer is 2m factorial. This is nothing but m plus n divided by m factorial. This m is for the n. Since they both are same, I've written m factorial twice, but I also divide this by 2 factorial. Why does this 2 factorial come up? Let's see with the help of an example. 10 men are to be divided into two groups, one consisting of 5 men and the other one also consisting of 5 men. So if I go by the formula, I have m is equal to n, m plus n is 10 again. So the formula is 10 factorial divided by 5 factorial divided by 5 factorial divided by 2 factorial. This is the answer. But why is this the answer? Let's solve it using combinations or using the NCR way. I have two groups. I have group number 1 and I have group number 2, and I have 10 people. Both the groups need to have 5 and 5 people. So the number of ways I can select people in the first group is 10C5, and here also I'll have left out 10 minus 5 people. So I have to select 5 people out of 5 people, which is 5C5. So here the answer is 10 factorial divided by 5 factorial divided by 5 factorial. Now you notice here that the 2 factorial has not come up as of now, but 2 factorial has to be there in the answer. Now I'll tell you why. For example, I chose A1, A2, A3, A4 and A5 in group 1, and similarly A6, A7, A8, A9 and A10 in group 2. Now notice here that these labels are not given to me, that who belongs to group 1 and who belongs to group 2. So these are not known to me. In one case, in 10C5, I will select these 5 people. Let's say this 10C5 represents this 5 for one case. In another case, in the second case, let's assume this 10C5 chooses these 5 people. So automatically, if I choose these 5 people, the remaining 5 go in the different group, or if I choose these 5 people, the other ones go into the different group. But both these cases 1 and 2 are actually the same. Why? Because I don't have labels to this group. That is why we divide here by 2 factorial. Now if you remember the previous question we did, there I had group number 1 and 2 also not labeled, but I had 7 people in one and 3 people in the other. So automatically the group's identity was in a way known by the number of people in that group. I can call the group with 7 people and the group with 3 people. But here, since both the groups have equal number of people, I am unable to make that distinction. What will I call them? The group with 5 people and the group with 5 people. So you will also not be able to understand that which person is in which group. And also mathematically, I've shown you that 10C5 I can select these people in this 10C5, or I select these people in 10C5. The groups being formed are same in both the cases, whereas it is counted twice when I take 10C5. That is why we divide by 2 factorial. So remember, this formula is really important. This is what they generally ask in examinations, and people forget to divide by this 2 factorial. If we had 3 groups, let's say I had 15 people and I had to divide them into 3 groups of 5, 5 and 5, what would my answer have been? It would have been 15 factorial divided by 5 factorial divided by 5 factorial divided by 5 factorial divided by 3 factorial. Okay, 3 here because I have 3 same groups. So remember this very carefully. Okay, let's move on to type 1, question number 3. Now the number of ways in which m plus n things can be distributed into 2 groups. The 2 groups are labeled A and B, containing m and n things respectively, such that m is equal to n. Now the answer is 2m factorial divided by 2 factorial divided by m factorial divided by m factorial. Now this is what the answer was in the previous case. But here what is the addition? That I multiply them by 2 factorial also. Now let's do this with an example. 10 men are to be divided into 2 groups as in the previous case. One consisting of 5 men and the other one also consisting of 5 men. The 2 groups are labeled as Chelsea and Manchester United. Since I am a football fan, so I use these 2 names. Okay. So now what is the difference from the previous case? That I have labeled these groups. I have Chelsea and I have Man U here. I have 10 people. Let's say I have to choose 5 here first. So I'll choose in 10C 5 ways. Out of the remaining 5, all of them have to go to Manchester United. So multiplied by 5C5, which is nothing but 1. So what is my answer here? 10 factorial divided by 5 factorial divided by 5 factorial. So if you pay attention to the previous slide, or if you recall the previous slide, you will notice that I was unable to name these groups earlier. I could not say that this is a group of 5 members and this is a group of 5 members. So it was confusing. I didn't know which group was what. Whereas in the previous case, I had 7 and 3. So I could easily say that I had 7-member group and a 3-member group. Okay. What labeling does is, now I can say that I have a 5-member Chelsea group and a 5-member Manchester United group. That is why the answer is only 10C5. Here also, if you look at, what will my answer be? 10 factorial divided by 2 factorial divided by 5 factorial divided by 5 factorial into 2 factorial. So this 2 and this 2 will cancel out. So what labeling does is it also gives me arrangement. So that is why I multiply by 2 factorial from the previous case, or you can simply solve using the NCR formula. Okay, so just keep these 3 questions in type 1 in mind and you will be through in most of the groupings question. And this groupings is asked a lot of times in all competitive examinations. Let's move to type 2. Type 2 is cases of balls and boxes, also very frequently asked type of questions. I'll move to the first question in type 1, case of different balls and different boxes. It means I have, let's take an example. In how many ways can 5 different balls, so let's label 5 different balls, B1, B2, B3, B4 and B5 be put in 3 different boxes. Let's say I have this box number 1, this is box number 2 and this is box number 3. What I've been asked is in how many ways can these 5 different balls go into these 3 different boxes. Okay, let's take this ball number 1. How many options does this ball number 1 have? Either it can go in the first box, or it can go in the second box, or it can go in the third box. So it has 3 ways. Similarly, the second ball B2 also can go in the first box, can go in the second box, or can go in the third box. So again I have 3 ways. Similarly for ball 3 I will have 3 ways, for ball 4 and also for ball 5. So what is my answer here? It is 3 raised to power 5. What was the case here? I had different balls and different boxes. So my answer is 3 raised to power 5. Let's move on to the next set. So the next case is, again we'll have balls and boxes. Let's see what the case is. I have identical balls and different boxes. So in how many ways can 5 identical balls be put into 3 different boxes? So I have 5 balls. Now I don't have B1, B2, B3, B4 and B5. I just have B, 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 B and B. These are 5 identical balls. But again I have 3 boxes, 2 and 3. Now just for logic's sake, this box number 1 can either have 0 balls or 1 or 2 or 3 or 4 or 5. Similarly this second box also, and similarly this third box also. But if this ball, let's say, has 3 balls, then what are the cases? Either the box number 2 will have 2 balls and box number 3 will have 0 balls, or both of them can have 1 ball, or this will have 0 ball, the box number 2, and the box number 3 will have 2 balls. But it will be very difficult if we start counting the cases. If I start counting, I'll have to assume, let's say box number 1 has 0 balls, then these two combined will have 5 balls, and then I'll have to form further cases and cases and cases. By the time for the examination would be over. Okay, so we have a easier way to solve this. Now what is the method? Look here. Let's say I draw 5 balls, 2, 3, 4 and 5. Okay, 5 balls as given in the question. I have to have 3 different boxes. For, let's say I place 2 partitions in these 5 balls. I had 3 different boxes, so I placed 2 partitions. Partitions will always be represented by these lines, and it will be 1 less than the number of different boxes. I'll tell you why 1 less. With these two partitions, I actually have created 3 spaces. This is space number 1, this is space number 2, and this is space number 3. So basically I have formed 3 boxes. Here in this case, box number 1 has 2 balls, box number 2 also has 2 balls, and box number 3 has 1 ball. Also the partition could have been like, I have 5 balls, one partition could have been here, one could have been here. Here box number 1 has 4 balls, box number 2 has 1 ball, and box number 3 has 0 balls. 0 balls. Okay, it's one and the same thing. You can draw anyways. Now let's go back to the permutation thing. Here if you see, I have how many things? I have 1, 2, 3, 4, 5, 6 and 7. I have 7 things which need to be arranged in a line, out of which 5 are one of the same kind, which are the balls, and 2 are of the same kind, which are the lines or the partitions. So in how many ways can I arrange these 7 things? This is given by 7 factorial divided by 5 factorial divided by 2 factorial. This is my answer to this question of the number of ways in which 5 identical balls can be put into 3 different boxes. So this here, the partition thing is just a method to solve. You just need to understand this method and just learn it on how to solving this. I've told you, if we keep solving cases like here, it will take us at least 2 hours to solve this. So this is a easier, just 1 minute method, probably less than a minute also. Okay, let's move on to type 2, question number 3. Identical balls and different boxes. Okay, so we are again at the same thing, but I have a different question. If x plus y plus z is equal to 15, then what is the number of positive integral solutions? This is the same case as identical balls and different boxes. So I have x plus y plus z is equal to 15. Okay, I have to find out the positive integral solutions. First I'll tell you how to solve only integral solution. Let's suppose that this word positive is not given. The formula for this is 15 plus 3 minus 1 c 3 minus 1. Now this is nothing but the same case as before. These 15 are the balls and these 3 things are the boxes. So if I have to draw 15 balls here, since I have 3 boxes, how many partitions will I draw? 3 minus 1, 2 partitions. So I'll have to arrange 15 plus 2 things in a line such that 15 are alike of one kind, which are the balls, and 2 are alike of one kind, which are the lines or the partitions. So in how many ways can this be done? 15 plus 2 factorial, which is 17 factorial, divided by 15 factorial divided by 2 factorial. So this is 17 factorial divided by 15 factorial divided by 2 factorial. Now if you are wondering what I have written here, this is the same thing. I'll tell you the general formula for this. Let's first solve this. I wrote 15 plus 3 minus 1, which is again 17 c 3 minus 1, which is 2. If you solve 17c2, this is nothing but 17 factorial by 15 factorial by 2 factorial. In a lot of books you will find the what is the number of integral solutions. The formula is given as n plus r minus 1 c r minus 1. Here what is n? N is this thing here, 15. What is R? The number of variables x, y and z. So this is 3. Minus 1 is minus 1, and here I have 3 minus 1. So this gives me 17C2. But what is the basis of this formula? Is just balls and lines, which we've already discussed. So most of the teachers skip this part, the explanation part, and just give you this formula. But now I've told you how this formula has come up. Okay, so now what was the original question? The number of positive integral solutions. Now mind you, this 17 factorial by 15 factorial by 2 factorial will give you cases like x is 0, or in other words, the box number 1 has no balls, and let's say y is 13 and z is 2. This case is also covered in this 17 factorial divided by 15 factorial divided by 2 factorial. But we need a positive integral solution, means x, y and z at least have to be 1. X has to be at least 1, y also has to be at least 1, and z also has to be at least 1. So I'll write 1 plus, 1 plus and 1 plus. So anything greater than 1. Or in other words, each box needs to have a ball. So this question can be reframed. Let's say there are 15 identical balls to be placed in 3 boxes such that there is at least 1 ball in each of the boxes. Both these questions are the same. How do we solve these kind of questions? Let's assume that capital X is small x plus 1, capital Y is small y plus 1, and capital Z is small z plus 1. Okay, so now I have made this x, even if now small x is 0, capital X will have 1. Okay, in other words, what I've done is I've already allotted x, y and z 1 ball or 1 number each. So if I've already allotted them 1 each, so the total from this side will reduce by 3, because x already has 1, y already has 1 and z already has 1. Okay, these are capital X, capital Y and capital Z. The notations don't really make a difference. So I have already have allotted them 1 so that at least 1 ball goes in there. So from here I'll have to subtract these 3 balls which are no longer available. I already put these balls in each of the boxes. So now I am reduced to x plus y plus z is equal to 12. Now this is the same case as before. I have 12 balls and 3 boxes. In how many ways can this be done? I can do it in 12 plus 3 minus 1, which is n plus r minus 1 cr minus 1, which is nothing but 14c 2 ways, or 14 factorial divided by 12 factorial divided by 2 factorial. The same thing. Okay, so this capital X, capital Y and capital Z denote that 1 ball is already in all the boxes. So if I've placed 1 ball here, 1 ball here and 1 ball here, so number of balls left with me are 15 minus 3, 12. So this is just a way to solve these kind of questions. Okay, let's move to this next type. Let's say I have identical balls and identical boxes. I have 3 identical balls, or let's take 5 only, 5 identical box in 3 identical boxes. In how many ways can this be done? The answer to this is 1, which is obviously subject to logic, because I cannot make out which box it is and which ball is going in which box. So just spend a little time on this and you'll find out that there is just one way. One way, or you can say no way, because you just can't place anywhere. Let's do some practice questions. Find the number of ways of selecting at least one object from 10 distinctly different objects. So I have 10 different objects. Let's label them as O1, O2, O3, O4, O5, O6, O7, O8, O9 and O10. Now I have to select at least one object from these 10. What are the ways I can deal with this object 1? Either I will select this object or I will not select this object. So I can deal with this object in just two ways. Similarly for the second object, either I'll select it or I'll reject it. Similarly for this third object, either I'll select or I'll reject. For the fourth one, and so on. So with each object I can deal in two ways. So what is my answer? 2 multiplied by 2 multiplied by 2 and so on 10 times, because I have 10 objects. So this is 2 raised to power 10. But this is not my final answer. Why? Because this 2 raised to power 10 includes the case wherein I reject all the objects. I choose this cross sign. So if I have to select at least one, I will just subtract 1 in the case where all are rejected. If I subtract this case where all are rejected, I get the cases where at least, this is the answer to, at least one object is selected. Now this was the case for 10 distinctly different objects. Now the second case is for 10 identical objects I have to select at least one. How is this different? Now all the objects are same. I have O, 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 O and so on 10 times. So what are the cases here? Either I can select 0 objects, I don't select any, or I can select one of them, or two of them, or three of them, or 4, or 5, or 6, and similarly I can select all 10 objects. So what are the number of cases in which I have to select at least one? I'll leave this 0 part. From 1 till 10 I have 10 ways to select at least one object, and the 10 ways being either I select one of them, or two of them, or three of them, or 4 of them, or 5, or till 10. Now don't confuse this with 10C1 and 10C2. This holds only when the objects are different. Okay, these all objects are different from each other, but here all the objects are same, so the only number of ways are 1, 2, 3, 4, 5 and so on till 10, representing the number of objects